So here is the, again, we can start it from here. So here is a big roadmap, and case 1, 2 are, again, I guarantee that calculation is very straightforward. And case 3 is the focus of the damped vibration systems. We want to put a little bit more energy here. So here I put the standalone. So here is called the underdamped. Single degree freedom vibrations. Okay. So for that case, we continue, and so if the root, in terms of your nodes, you can continue by taking over, continue from there. So basically, P equal to P1, P2. So from here, we really solve for that one. So basically, from here, you can imagine is this minus C over 2M and plus minus. So because this is negative, we're expecting they have the certain complex number will coming up, okay? And not to make the things complicated, so let me use the black box, okay? And everyone know what I'm doing. Or otherwise, if we pick these items here, then basically using this template, or we can express it into that one minus zeta omega n plus minus. Okay, right now zeta square divided minus 1 equal to negative. So if this one is negative, you look at that one, compare. Right now you compare these terms with what I'm going to write here carefully. Because right now the square root in that expression is negative. So basically, complex numbers multiply omega n. If that is negative, I simply swap the orders and become the negative, become positive. Okay? Any questions? Okay. So that is our characteristic root. Okay. So if we have this root, and if you remember, so right now I'm going to write up the solutions. Okay, the solution is this. So basically from here, before we write up the solutions, and we can put the certain anatomy here. So this one is our real part of the roots, and this is the imaginary part. Right? And put the things easier, again, here we review. So say if we have a characteristic root is A plus JB, okay? And if we want to express this term, then basically we put is E and A plus JB T, right? And here we distribute EAT multiply with EJBT, right? Okay, so that one is EAT multiplied with this one. Again, if you remember, we have a definition is E theta IC J theta equal to cosine theta plus J sine theta, right? That is we call the definitions. Okay, so here we simply plug in, so that becomes cosine BT plus J sine BT, right? We simply plug in here. So that means right now A is our real part, so put into here, so therefore x of t will be equal to exponent of AT, and A is our real part, and that is minus zeta omega nt. You good? Right now what I'm doing is the first most important things in ME408. So listen carefully, okay? So that'll be okay. So right now you simply plug in the corresponding number to here. Okay, this expression is easier to watch, right? Okay. And now let me before doing that one, let me add it up one more line. So let me do this one. So basically again, we going forward is if we have this one, then our solution basically is A1 exponent P1t plus A2 exponent P2t. Yeah. So add it up. I think we need to add up this one prior to this one. Okay. So now for the P1t, basically that is I plug into here cosine. What is B? B is our imaginary part. And so why not, to reduce our writing, so why not I define something, let me define the whole thing let me define as omega d. And I will explain to you what is omega d, but let me define the symbol and help us reduce the writing on the figures here. Okay, so here is omega dt plus I sine omega dt. So that is P1 and plus, okay, and plus right now the second term, so that is A1 here, and multiplies A1. So this is A2, E minus. So for the P2 is minus the conjugate part. So again, the real one. Again, we're still using this template. Can you follow me? P1 equal to real part plus J imaginary part. So real part and imaginary part. Okay. The same thing for P2 is the real part minus the imaginary part. So this is the real part and minus. Okay. So that is the four expressions based upon this. And right now you can see in the summation of the two terms, they have a common term. The common term is exponential functions of this here. So let me take exponent functions out. The remaining will be once you are writing, you can see the remaining basically is a combination of A1 times cosine, A1 times sine, B2 cosine, B2 sine. So basically I want to combine the coefficient for cosine functions. So here is cosine omega dt. And we have another term is sine omega dt, right? For the term omega d, for the term of cosine omega dt, that is a combination A1 times something plus A2 times something. Overall together, let me define this as a C1, whatever, because we're still going to solve for those unknowns. I just arbitrarily define the constant. The similar way, the A1 multiplied with I, that is a coefficient for sine, and A2 multiplied with minus I, that's coefficient for sine. Again, combined together, I simply define it as a C2. C1, C2 may be real, may be complex, and depends on the situations. Mathematically, it's possible C1, C2 can be complex, but in physical, for vibrations, I can tell you C1, C2 both should be real numbers. Okay. But here that is in the side talking okay. So right now in this way you can see how many unknowns we have. C1 and C2 are the defined unknown constants, so we have two unknowns. Zeta is the numbers we can determine from the given information. So zeta is a constant. Damping coefficient is a constant. Omega n, again, from there we know that is constant. Omega d here, appear here, that is derived from here, so omega d is also constant. So in here, in only two unknowns is C1 and C2. And that can be solved with the initial conditions here. Okay, so keep that in mind, and let me do one more expressions. And you know that, and before we know that when C1 cosine 80 plus C2 sine 80, if you remember a couple lectures back to, this one can be also have equivalent expression, say, for example, the cosine 80 minus phi, right? And we may have another expressions is sine 80 plus phi 0, right? Do you remember this form? So it really depends on which way you like. And let me pick up this one. How about that? So here is E minus theta omega nt, and with certain combination that is capital X and cosine omega dt minus phi. Let me pick up this one. So again, in this way, the two unknowns is this. Okay, so here I highlight are the two unknowns that can be solved by using the initial conditions. And again, we will have the numbers, and the numbers will be ready. So let me erase this one here. So now I want to, based upon this one, this is the general expressions of the solution for underdamped system. And let me rewrite here. So basically for underdamped vibrations systems, damping ratio less than 1, we have the general solutions is like this. E minus theta omega nt times x times cosine omega n minus 1 minus theta square omega dt minus 1. Okay. So here I simply copy that form to here. I want to give certain explanations what this form representing. So from here you can see the first one we can put some kind of analysis and about what means of each term. Basically, in these solutions, there's a multiplication of 3 terms: exponential functions, a constant, and x representing the amplitude, and with the sinusoidal functions, cosine or sine, either way. Okay. So this one, basically, this term representing is the oscillations. This term showing is the oscillations nature behind, right? So from here, we know the solution will oscillate in certain way, right? Before we put into graph, we know it. And oscillation, furthermore, we can know this oscillation will be or vibrating with frequencies equal to how much? From this expression, we can also know it. The frequency of the sinusoidal function basically is given by this one, right? Omega d. And usually we are expressed by radians per second, right? Okay, so in this way, omega d is the vibrating systems of a damped system. It's a vibrating frequency of the damped systems. So that means omega d, sometimes we define it, we say this one is called a damped frequencies. And be precise, we call it damped natural frequencies. Okay, so that's called omega d. And compared to omega n, that by definition is k over m, and for calculation, this one is we call the undamped natural frequency. Okay, so before we always say omega n is the natural frequencies, but here we need to be more precise. This is called the damped, and this is called the undamped. Okay, so from this point onward, And for any testing or any homework, I will be very specific and asking, say, which number I really want is omega n or omega d. Then I would say undamped natural frequency or damped natural frequency. So here you need to pick up the right terms, okay? So we know this oscillation will be in the frequency omega d. So from here you can see omega d by definition is this one. Omega d is related to our natural frequency, the undamped natural frequency omega n here. Also is governed by the damping coefficients, right? So the magnitude of the damping coefficient will affect the oscillation frequencies here. Okay, so that is the first thing is for the damped vibrations. Once we have C or we have the zeta here, if that system is underdamped, then again its vibration frequency is really governed by this number as well. So before we doing something, you need to have some kind of pictures. Okay. The two terms together simply is a certain amplitude, and the amplitude representing really is the amplitude of these oscillations. However, this amplitude is not constant anymore. However, it is time varying constant. In precise, this is exponentially decaying amplitude. So this is the time. Okay, so with the two things and together, again, this is not new because in our review we've done this similarly before, right? Okay, so now I'm going to put the things on this drawing. The more time I spend on a topic, that means the topic is more important. Okay, so for God's sake, and more exercise will be on the homework, and likely more chance will be on the test. Okay. So here is our XT. So with those kind of detailed, I would say formulations of the information, then we can plot. So I'm going to plot the oscillations, and we know the oscillation is with a certain frequencies of the cosine, and with the phi, that is the phase angle. And also this oscillation is confined within the amplitude, and the amplitude is follow up this kind of exponential decay. Okay. So this one is x times exponents minus zeta omega nt. So those are the exponentially decaying functions, and starting from this value is capital X here. Okay, so that is starting from X. So from here we can begin to draw the oscillations. So that's the sine function, the cosine functions, or sine, either way. Okay, so from peak to peak, that define is our period, or from here, I don't want to overlap with my drawing, so we can also define the period is from valley to valley. Okay, so what are we doing here? So this is the period. Okay, so period by definition equal to 2 pi divided by frequencies. Okay, in precisely, yeah, we just did it. You good? And anything else we can talk about? I think that is I think. Yeah, I think that's it. So that we can take a break here.